All right, stat students. So we got a pretty busy lesson here today. There's a lot of videos that we're going to be watching in this lesson, so I'm excited about it. But we're getting into a topic that I hold near and dear to my heart, which is probability. There's a lot that can be learned and applied to real life. So hopefully you gain a lot of understanding about the world from this chapter. Again, it's absolutely one of my favorites, just because your eyes are sort of open to how things function in real life. Okay, so this one is very applicable. So we're going to go ahead and get things started. Okay, so go ahead and in your notes you need to start a brand new page. Call it Unit 4, Chapter 5. You'll notice that we've skipped Chapter 3. We come back to that next semester. Actually, it's one of the last chapters we do. But we're going to be talking about probability. Okay, so lots going on in this lesson today. We're going to begin the lesson with the... Hold on, let me move my headphones here. We're going to begin this lesson with the idea of probability. And we're going to write down some notes. And then we're going to watch a video here in a second. All right, so the idea of probability. So a lot of you understand probability as a percentage, right? You've probably done exercises with in a math class where you were rolling dice or spinning a spinner, something like that, flipping a coin even. And we're going to get to that stuff, but we go a little bit deeper here. And at this point, a lot of you are mature enough to have an understanding of what we're about to get into. But this introduction is so important for your understanding going into the real world and how things are actually functioning. But we're going to go ahead and start with this idea of probability. We'll start with our definition of probability. And we're going to write down two definitions here in a second, but let's go ahead and go to this right here. Okay, see the idea of probability. Probability, and we'll start at the bottom here. It says it's the probability of any outcome of a chance process is a number, and we'll write, really we're just going to write all of this here. I don't have it highlighted in my screenshot, but that's fine. Of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur over a very long series of repetitions. Okay, so something new, and I want you to underline this, a very long series of repetitions. Okay, very long series of repetitions. This is going to be the key idea for us. It's so important that you guys understand this idea of long series of repetitions, okay? Because we have up above this new rule, which I'm not going to pause this yet. If you're waiting for me to pause the video, give me a second. We've described what probability is, but here's this new rule. It's called the law of large numbers. So we're going to write that down. Give yourself some space underneath probability. So law of large numbers. Okay, so the law of large numbers, and we have this definition here. It says if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. Okay, this is what we want. This is how our probabilities are created. So we've kind of already done this in this class when we had the dice rolling. We're going to get back into that, the simulations on our calculator. So we're going to pull that up probably next lesson. We won't get to that this lesson because we've got just too much to do in this one. But if you think about what we've done on our calculator with those, we made those normal distributions of the dice rolls. Well, we created probabilities there. That was 2,500 rolls. That is a large amount of repetitions. Okay, so before we start watching a few videos, I want to write down a couple other things, because here's the issue. Here's an issue that a lot of you may have, but I call this class. Let me say this. I kind of like this class because it gives me a chance to teach young folks about gambling, okay, and the issues with it. Now, I don't gamble. All right, I do not gamble at all. Let me go full screen for this, so you can see me. So I don't gamble at all. One time, I happened into $20. Like I got it for free. Somebody gave me $20, or I came into $20. So what I did with that $20, I was like, you know what? This isn't really my money. I don't feel like I deserved it. So, and I don't think I did, but they gave me $20. I was like, you know what? Let's go buy a lottery ticket. Okay. Let's get the big ones too. I want to try to win big money. So I go into the gas station. I get two. I think I said, what's the most expensive one you have? And he said $10. So, okay, sure. $10 on lottery tickets. So I buy two of them. I go to a friend's house and I'm like, hey, I got these lottery tickets. Do you want to help me? You want to scratch them, see if I can win anything? So I gave him one. I had one. We lost. Okay. And that wasn't like a defining moment for me. I knew that the odds were bad, and I don't spend money on lottery tickets. Some of you may have parents that spend money on lottery tickets, or that's just something that is normal for you. But this class is really going to tell you why you probably should not do that, okay? And how you're kind of just throwing away money, because that's essentially what happened. Was I just lost money for nothing, right? Like I threw away that money. I could have used that for gas. I could have used it for groceries. I was in college at the time. I really shouldn't have done that. So it was definitely something I'll never forget, but I should not have done that. So we're going to be talking about some of the myths that a lot of, especially young folks, and really what the lottery wants you to not understand are these myths here. So here's the big one here, the myth of short run regularity. So here is this myth. Here's where we start. These are facts. These aren't myths, but this first sentence is a fact. Randomness is predictable in the long run. So over a large repetitions, that law of averages. Okay, the law of large numbers. Law of large numbers means, and we need to write these in our notes. Hold on. So let's form our notes a certain way here. So we're going to draw a line in our notes before we write this. Whatever, I'll use a green line, sure. So we're going to write these in our notes, and we have myths. So the first myth is short run regularity. Okay? It's this idea that randomness is predictable, or that randomness is predictable in what we call the short run. So here it starts off, the idea of probability is that randomness is predictable in the long run. Our intuition tries to tell us random phenomenon should also be predictable in the short run. So, however, probability does not allow us to make short run predictions. So if you've ever played a board game where you roll dice, which if you were a face-to-face learner at one point right before the quarter changed, we did play a board game with number cubes or dice, and a lot of you'd roll and you really needed a number to happen, like you wanted to roll a 2, and you kept rolling other numbers, like, okay, it's got to come up at some point, right? Like I have to be getting this soon, okay? But it doesn't work that way, okay? And we'll describe that more as we keep going. But to help illustrate this, I have a video clip from a TV show, Friends, that we're going to be watching. So my wife is a big fan of Friends, the TV show. I'm pretty sure she's watched it at least 20 times. So in this show, they have an episode where they're in Las Vegas, and one of the characters named Phoebe, if you are familiar with the show, so I'm going to go ahead and show sort of set this up here. Phoebe is playing on slot machines, okay? And the idea of a slot machine, you just put it in, you pull down the lever. That is and now all these things are cycling and circling. That is a random occurrence, is what's happening. It's the same idea as flipping a coin, except it's a little more fun because there's sounds and there's lights flashing. This one looks not as like nice as modern ones. Of course, this show is like in the late 90s, but so she's there just playing, and then we have this idea of someone who's called a lurker. Okay, so let's go ahead and watch the clip, and we'll talk about the lurker. Here we go.
Get out of here, you lurker! Go on, get!
Hey, peeps.
You made up!
Yeah, I couldn't be mad at him for too long.
Yeah, she couldn't live without the Chan love.
Okay, get a room. We have one.
I know, use it. Oh, well, lost again. That's it, you and me, outside.
I wouldn't want to see you lose a chunk of that pretty blonde hair.
Be cool. Okay, lady, your lurking days are over.
What?
Yeah, from now on, everyone you lurk, I'm gonna lurk first. If you move on to someone else, I'm gonna be one step ahead of you every single time. And then I'll be on your ass every hour of every day till Monday. Because that's when I go home. When do you leave?
Also Monday.
What time? Maybe we can share a cab. Take a hike, Took.
Excuse me, sir. This lady played my quarter. This is my money.
Is that true, miss?
Sells drugs to kids.
What?
She sells drugs to kids.
It was my quarter.
Was it her quarter?
How about we talk about this over dinner?
Okay, lady. You're out of here.
No, you can't arrest me! No, I won't go back! I won't go back to that hellhole!
Just taking you outside.
Oh, okay.
Okay, so let's talk about this video as it relates to this right here, this myth of short-term regularity. So as hilarious as this is, and this is made for comedy purposes, I truly believe that there are people who will lurk at a slot machine just like this lady because they do not understand this idea of short run regularity. Okay, so right here, our intuition tells us that random phenomena should be predictable in the short run. So if you're the lurker is watching Phoebe or this man, which actually worked out for them, play, not winning. So in their minds, they're thinking, this machine is about to win. Like they're going to get off, and I'm going to play their machine because I think that it's going to win at some point pretty soon because they've taken a lot of the losses for me, and now it's my turn to get a win. Okay, this rule here is something that they don't understand, which is this idea that no matter what happens before, that does not affect what is going to happen next. Okay, and one of our definitions of probability that we'll get to maybe I think the next lesson is this idea of independence. These are independent events. Each time they pull the lever on that, it's going to be independent of what had just happened. So right here it says probability does not allow us to make short run predictions. So they've only been playing for a few, maybe they watched that guy for 10 minutes, 5 minutes, and then he left and moved on, however long he played. Even though that seems like a lot of play times there, it still doesn't matter necessarily. Like, they're not going to be able to make these predictions of this behavior of these slot machines, okay? Every time they pull it, it's just like rolling dice. You don't know what's going to happen next. There isn't a way to predict it, is basically what this rule is saying. So then the next rule we have is this law of averages. So we have short run regularity, and then law of averages. Okay. So random behavior evens out in the long run. So this rule here is what casinos, lotteries all make their money on. Okay. Future outcomes are not affected by past behavior. So that's what we talked about with them. Past outcomes do not influence the likelihood of individual outcomes occurring. So yeah, here's that definition that I was just talking about, independent, which we're going to define a little bit more later. So this random behavior evens out in the long run. And this is how casinos make money. They know the probability that somebody will win at their slot machine. Okay? They know the odds. And they know that over a year's time, when they have thousands of people play on these slot machines, they are going to make money off of it. Otherwise, they wouldn't be in business. So here's the thing. Lotteries know this as well. The lottery ticket that I bought, when I bought that, $20, I bought 2 of them. The people who designed that card knew they were going to make money off of it. And I sort of fell into their law of averages there. I was on the average side that says they don't win money. Okay? So that's something to keep in mind if you're like, oh, I'm going to turn 18 and I'm going to go buy a lottery ticket. You're going to lose money almost always. On average, you are losing money. Okay? Sure, some people do win. Okay? Now that's a whole nother psychological thing that could be discussed, but we're not going to. Okay? We got another video that we want to watch talking about everything that we've just discussed. Okay, so this one's going to be a little bit longer, probably about 5-6 minutes. I'm going to pause it, and then we'll come back to it again in a second. But we're going to write down some more definitions. Okay, but I'm going to go ahead and we'll get this video started. It's introducing probability, and a lot of the definitions we've written are we already have. So I may pause this and chat mid-video. But I'm going to go ahead and play it. Against All Odds is the company. I think we've watched one of these before. Yeah, we have. They did the smoking causation video. Let's go ahead and watch it.
Hello, I'm Party Sabetti, and this is Against All Odds, where we make statistics count. Predicting the future sounds like the job description of a fortune teller, but there are lots of times in everyday life when you'd want to do just that, without using a crystal ball. Rather than just pulling guesses out of your hat, probability is the mathematical way to make these kinds of predictions. A 50% chance of snow, a 20% chance of complications from surgery, a 1 in 175 million chance of winning the lottery. You encounter chances like these all the time in daily life. What the heck do they really mean? They're attempts to quantify uncertainty, something we do all the time when we're trying to make predictions in the real world. For instance, I start my mornings with a forecast of the future, in the form of a weather report. I just want to know if I need to bring an umbrella with me. For meteorologists, a question like that boils down to probability.
Mount Washington Valley northward, a thicker cloud cover. There is the sunshine we're seeing drift in here over the next...
When TV weatherman Kevin Skarupa issues his forecast for the residents of New Hampshire, he doesn't know for sure what's going to happen. Weather is an example of a random phenomenon. It's an event with an uncertain outcome. But it does have a regular pattern over time. Nature is predictable and systematic, and he's tracked these patterns before.
If we're to make a winter forecast, for instance, we'll look at the last couple of years. We'll look at where the patterns are going to be now. We'll look at what the 30-year average is. We'll look at what the highest has ever been, what the lowest has ever been, and take all that into consideration to have a really good sense as to the overall picture for that particular location.
Today's meteorologists rely on multiple, complicated mathematical models to make their predictions for the public. The models churn through tons of weather-related data points and update several times a day.
It is weather balloon information, which goes up at the exact same time of day at all the National Weather Service sites. And as they climb up through the atmosphere, pick off all that weather data. It's surface observations. It's what's going on at that moment as far as humidity, wind, sky conditions, temperatures.
The models combine all these weather inputs to create maps of what they predict will happen this time based on what they've seen happen in the past when similar scenarios were observed. Over time, the weather exhibits patterns, but for any one particular instance, it's not completely predictable with perfect accuracy. That's why forecasters talk in probabilities, even if the public doesn't really understand what a probability like 70% chance of rain means.
When a station will put 70% chance of rain, it means that 70% of the viewers, if equally spread out, will see that precipitation that day. That essentially means coverage, I guess is the best way to look at it.
So in that case, the forecaster feels sure that 70% of the area will see rain that day. but meteorologists are usually expressing a combination of degree of confidence and area coverage. So they're also using that percentage number to try to quantify the likelihood of precipitation at all. This one probability number does double duty. It's called on to express both aspects of the forecast, confidence and coverage. No wonder we, the public, get a little confused about what our local weather person's getting at. But as the mathematicians work to refine the computer models, and meteorologists like Skarupa work to communicate their predictions more clearly, forecasts are constantly improving.
Back when I started, snow starting in the afternoon was a logical forecast, and a 3-day extended forecast was the norm. Now it's people kind of want to know what hour it's going to start. And so the bar has been raised for us at the same time while the maps continue to get better. Certainly plenty colder than what we have been over the last 4 or 5 days. Then a look toward the weekend ahead.
The probability of any event is the proportion, or percentage, of times it would occur in a long series of repetitions. Random phenomena like weather events aren't chaotic. They're unpredictable in the short run, but have a regular pattern in the long run. They're not random in the sense of having no rhyme or reason. It's important to understand the concept that this kind of chance behavior is unpredictable in the short term, but has a regular and predictable pattern in the long run. Take the example of flipping a coin. The toss can come up heads or it can come up tails. Our first toss is tails. Let's record it on this graph of the proportion of heads we get. The next toss is heads, so now our proportion of heads to the number of tosses is 0.50. Next comes 2 tails in a row, dropping the heads proportion to 0.25. The proportion of heads is pretty variable at first, but over time the proportion of heads gets closer and closer to 0.50 and stays there. The same thing happens if we run a second trial. This time we get a bunch of heads in the row at the start, but over time the proportion of heads hovers right at 0.50. We don't know what's going to happen on any one toss, but over time we can predict we'll get this proportion of heads and tails. As on this graph, we always assign probabilities a value between 0 and 1. Events with a probability closer to 0 are less likely to happen, and those with a probability closer to 1 are more likely to happen. Our 0.50 probability for heads in a coin toss means that either option is equally likely, 50-50. When you're talking about the probability of a giant asteroid slamming into the Earth,
all right, we'll start back at this part right here. So let's discuss what has been said. So one of the big takeaways here is this idea. Maybe you've never heard about it, but the idea that weather, 50% chance that it's going to rain, right? What does that mean? Is that like flipping a coin? We know it's 50-50, right? Or they said 70%. No, they talk about this idea that probability for weather is coverage, right? Or think about last unit we did when we did those probabilities under a normal distribution, area under the density curve. Think about it that way, Probability can be related directly to area, okay? Coverage in a certain area. So if they say that there's a 70% chance of rain in Smyrna, they're saying, okay, the population, 70% of the population will see that precipitation. I'm just sort of rephrasing what the meteorologist said, okay? So hopefully that makes a little bit of sense. That's how they're able to make these predictions, okay? And they're drawing on models of long-run data to get these predictions, okay? Now, we're going to write down another section here in our notes. And we're close to finishing this lesson, but we still have a few more things to get to. So I know that this one's going a little bit longer than I like. We're already at 24 minutes, but hopefully you're feeling a little bit engaged. I've got several videos. We're mixing it up quite a bit today. We have this idea of, let's call it practical. I spelled that wrong. Practical probability. This is how we can use this in our own lives, because like the lottery, we can figure out those probabilities, and actually I'm pretty sure they have to post them. I think on the back of lottery tickets they tell you your odds of winning, and so you can go into it knowing what to expect. People will do it anyway, but people that buy lottery tickets typically are not educated on probability, So if they look at it, they don't even know what it means. They just know that they have a chance to win a lot of money. Okay. So I'm trying to educate you all today on how to understand how these probabilities work. So practical probability, what I'm really getting at is like meteorology, right? Like that is a practical use of long run probability. And what they're using there is called a simulation. Okay, simulation. So let's write down a definition for simulation. This is an important idea, and we've actually already done simulations in this class. I've just not called it that. Okay? So a simulation is imitation of chance behavior based on a model that accurately reflects the situation. So think about this. Meteorologists use simulations, or they have the models of previous data that are going to help them model what's about to happen with the weather. Okay, it's an imitation of how it's going to behave. So it sounds pretty complicated to actually, in my opinion, I don't know really much more than what the video showed about meteorology, but it seems pretty complex. Now, another type of simulation would be random numbers. So right here, physical devices, technology. We have simulated rolling dice. And we're going to do that again this chapter just to really drive that home. But we have done simulation already in here using technology. Let's talk about some more practical applications of this. So let's do some examples here. All right, examples that can be used in real life. And we're going to watch videos for each of these. First off, we already did weather. We've already watched that video. The next one is going to be asteroids and meteors, which I think meteors are the ones that cause trouble for Earth, but I'm just going to use both of them. I'm not an astronomer. I'm not an astronomer. I think that's the right one, not astrology. I always mix those up. But this is actually one of my main fears. Extraterrestrial doom. I really am always concerned that we're going to get hit by a meteor. I really am. It's kind of a strange thing. Like heights, I'm okay with. I can't jump off heights. Not afraid of ghosts. Most times snakes and spiders don't bother me. I don't have a fear of most fears, or public speaking doesn't scare me. But like thinking about collision with an asteroid from outer space kind of freaks me out. Okay. So we're going to watch the rest of this video. It's going to be talking about this idea of an asteroid hitting Earth and how NASA and people who are in these observatories help make predictions of, are we going to get hit or not? So if this freaks you out, I understand. Let's go ahead and watch the rest of this.
Talking about the probability of a giant asteroid slamming into the Earth, you want that number to be pretty darn close to zero.
Yes,
Luckily
please.
for the rest of us, NASA's Near-Earth Object Program is closely monitoring asteroids with the potential to do serious damage to our planet.
Asteroids are very diverse objects. They run the gamut from ex-cometary fluff balls that you could break apart with your bare hands, to rubble piles that are held together by little more than their own self-gravity, fractured rock, slabs of solid iron.
While near-Earth space is home to over 9,000 known asteroids, only about half of them are large enough and have orbits that come close enough to the Earth to classify them as PHAs, potentially hazardous asteroids. Scientists around the world are keen to track these PHAs as closely as possible to figure out if any of them are on a collision course with the Earth.
When an asteroid is first discovered, we only have a few observations. As we add observations to the data set, the possible set of orbits gets smaller and smaller. That is the uncertainty region at any given time. As we add data, the uncertainty region will get smaller and smaller.
As the scientists refine the predicted orbits of the asteroids, they can start to work on computing the probability of a collision. They try to calculate the percent chances that any particular PHA will hit our planet.
The poster child for near-Earth objects is an asteroid we call Apophis. It's an Apollo-type asteroid, and it's coming very close to the Earth in 2029. Just a few Earth radii above the surface and well below the altitude of some of our communication satellites. It'll be a naked eye object in April 13th, Friday the 13th in 2029.
Now, when it was first discovered, we didn't know how close it would come to the Earth. In fact, the uncertainty region during its passage by the Earth was so large that the Earth was right in the middle of it. And as we got more and more observations of the asteroid, we're able to see that that uncertainty region no longer intersected the Earth. So we know that Apophis will pass by in the year 2029. Very close, but it will not hit.
Well, that's certainly good news, but it's not the end of the story. Apophis's close encounter with the Earth's gravity in 2029 will bend its trajectory, which makes the job of predicting where it will go from there much more difficult. If Apophis were to skim by the Earth on one particular orbit, the threat level goes up once again.
If it should happen to go through this little keyhole, which is very narrow, only about 600 meters wide, it will receive a gravitational boost just in such a manner that it will come back and hit the Earth in the year 2036.
Based on the latest observations and updated data, researchers have now effectively ruled out the chance that Apophis will be on that one specific gravity-boosting route. So the probability of a 2036 impact has plummeted towards zero. But scientists still scan the skies for other near-Earth objects with collision probabilities closer to 1, since even a small object's impact has potential for great destruction.
It would cause significant regional damage. It wouldn't be a global problem, but it would, if it hit on land, it would certainly reduce a large region to rubble. And if it hit in the ocean, which is more likely, of course, it would cause a tsunami, so that the surrounding coastlines would be in trouble, or at least the low-lying coastlines would be in trouble.
Researchers continue working on strategies to deflect an asteroid before it can cause big problems for us Earthlings. Just ask a dinosaur how deadly an asteroid impact can be. For Against All Odds, I'm Party Sabetti. See you next time.
Nice. Okay. Whew. Lord, that just gives me anxiety. I don't know about you guys. But again, extraterrestrial doom is my biggest fear. But isn't it like relieving that, you know, if you think about it, there are people that have the job to do that, you know? Like, that just sort of makes you feel comforted, right? That there are people who are watching for meteors. The science baffles me. The math behind it is incredible. So don't know how you're able to do that in space. Space is just always something that perplexes me, but it's impressive. No doubt. So think about this. They're able to use minimal data, and they're able to get these single number values. So let's go back to this. This single value, which for them, this idea of large numbers, so they keep gathering data, and they have this uncertainty region of will it hit Earth or not, and that's this idea of this single value, and they're trying to approximate it as close as they can, but they need more observations, more data to get this idea of this, will it hit Earth or will it not? And thank goodness it looks like it's not, and it's not going to hit that little keyhole that's going to send it back in 7 years to hit us. So that's really good. But this is a very practical application. Now, it is very unlikely that you're going to be doing this for NASA. That's fine. It would be something that would be extremely impressive if you're able to understand all that and get to it. But or even meteorology. I know that is more likely for a lot of us to get into meteorology. But something that is going to affect us every single day, and all of you every single day as you're watching this video. I upload this video to YouTube. Another very practical application of probability that is so influential is social media. I want you to think about this. If you have not watched the Netflix documentary called The Social Dilemma, for me it's a little dramatic. And I know a lot of you, there will be people who just don't agree with anything that it's saying, and that's fine. And I'm not here to push any sort of like political thing on my students at all. I'm never that way. But I think it brings up an interesting fact that if we're able to track asteroids, right? Like think about that. If we're able to track asteroids that are thousands of miles away, you know, and we're able to make predictions about that, and then also weather, we've got that mastered. How difficult would it be to make predictions about you based on the data that's collected, right? So I've got the trailer for this Netflix documentary. We're going to check this out because it sort of gives you the overall scope of what's in this documentary. And you don't have to watch it if you don't want to, but it's The Social Dilemma. I thought it was very profound. I didn't agree with everything in it, but it's something that is probably worth a watch, especially for youth such as yourself. But let's go ahead and watch this trailer.
When you go to Google and type in climate change is, you're going to see different results depending on where you live and the particular things that Google knows about your interests.
That's not by accident, that's a design technique.
What I want people to know is that everything they're doing online is being watched, is being tracked. Every single action you take is carefully monitored and recorded.
A lot of people think Google's just a search box and Facebook's just a place to see what my friends are doing. What they don't realize is there's entire teams of engineers whose job is to use your psychology against you.
I was the co-inventor of the Facebook like button.
I was the president of Pinterest,
Google, Twitter, Instagram.
There were meaningful changes happening around the world because of these platforms. I think we were naive about the flip side of that coin.
We get rewarded by hearts, likes, thumbs up, and we conflate that with value and we conflate it with truth.
A whole generation is more anxious, more depressed.
I always felt like fundamentally it was a force for good. I don't know if I feel that way anymore.
Facebook discovered that they were able to affect real-world behavior and emotions without ever triggering the user's awareness. They are completely clueless.
Fake news spreads 6 times faster than true news. We're being bombarded with rumors.
If everyone's entitled to their own facts, there's really no need for people to come together. In fact, there's really no need for people to interact.
We have less control over who we are and what we really believe.
If you want to control the population of your country, there has never been a tool as effective as Facebook.
We built these things and we have a responsibility to change it. The intention could be, how do we make the world better?
If technology creates mass chaos, loneliness, more polarization, more election hacking, more inability to focus on the real issues, we're toast.
This is checkmate on humanity.
Okay, so now it got pretty extreme there at the end, and I'm not here to say that what it was displaying is true. You can disagree with that all day. It's totally fine with you. But I want you to think about this. If we can track a meteor that is so far away from our planet, and we've figured out how to do that. If we can track weather to get rainfall within an hour, do you think it is possible that they can track you, gather all your data, as that video just showed? They have thousands upon thousands of data points based on you, based on what you do on social media, that they can use that to make predictions about what you will like. Yes, absolutely. That makes complete sense. And when I saw this video, that was something that stood out to me. Yes, it absolutely makes sense that they are able to, let's go back to this, get more repetitions of a chance process. Oh, what does this person like? Okay, what does Mr. Woods like on his social media? What videos is he watching on YouTube? Facebook, what information does he keeps him on the screen the longest? Okay, and they know which ones what I want to see. They're going to try to make me click on a link. It's called clickbait for a reason, right? Like, they know exactly what you want. Now, if they put things that I don't care about on there, I'm not going to click them, right? And that's how they say this machine is designed. It is developed with this idea of probability in mind to keep you on your phone as long as possible so that you can see advertisements, okay? And it doesn't care how it does it. So it's a very interesting watch to look at that. But I think that is probably the most practical use of probability today, okay? And it's so important that you guys going into the future understand how these things are designed, okay? Again, I'm not here to make a political statement. I'm just here to enlighten you guys about how statistics is being used in real life. This is very important that you understand this more than ever in human history. And this sounds super dramatic, but again, it is very important. So what we're going to talk about now is this idea of, and this is the last thing we're writing, experimental. Let's go ahead and let's draw a line. Okay. So we have experimental versus theoretical probability. Boy, what a lesson. 40 minutes in, and we've done quite a bit here, but it's been really good. This is, again, one of my favorite topics. So let's start by writing down experimental probability. So an experimental probability is everything that we've just talked about. The asteroids, the weather, social media, all of that is what we would call theoretical probability, okay? Or excuse me, experimental probability. Whoops, experimental, okay? Now you don't have to write these just because we already wrote them. Ooh, actually write this one here. Sports predictions, gambling, we'll talk about that in a second, but here we go. Probability that is determined on the basis of the results of an experiment or simulation repeated many times, okay? So if you think about it this way, you going on Facebook, which most of y'all, I think most of you Gen Zs and my students don't go on Facebook. It's more for old people like myself. But Instagram works this way. TikTok, I believe, probably does. But I don't have TikTok, so I don't know. But they're gaining results repeated many times, and they're building those behavior patterns for you. Okay? And they're creating the experimental probabilities. And the computer is so smart that it can do it. They've programmed this computer and built it so that it's able to make these predictions that a human could not make, okay? And that's just how smart computers are getting. So let's talk about the sports predictions. March Madness, every time that happens, such a fun time of the year, which, unfortunately it was canceled this year due to COVID, because March is when all of that went down. But if you're ever wondering, like, how did they come up with odds for Vegas, right? Like, how is that done? Okay, well, they have a statistician, somebody who understands probabilities, that's creating those. It's not random, okay? They make these probabilities so just like a casino, so they can make money off of them. They're expecting to make money. Obviously, you get to pick who you want based on the Vegas spread, but a lot of times they can sort of dial into who is going to win the game, who is favored. That's based on probability, experimental probability. There is no way for you to know the probability exactly that a team is going to win because there's just too much variability. A player could get hurt. There's so much that goes into it that it's almost impossible to get a exact, but you can come up with a close estimate. That's this whole idea. You have that uncertainty region, like with asteroids and meteors or weather. You have some uncertainty in it, and that's okay. All right, so that's going to be the big takeaway here. Now, go in the other direction, which is what we're going to be focused on in this unit more than anything, is this idea of theoretical probability. Essentially, this is what should happen. Okay? If we think about it. So, you've always heard, if I take a coin and I flip it, what's the probability it's going to land on heads? Well, in theory, 50%, right? Okay? Now, the diagram, the video that we saw, let me go back to that. Let's see, where's that coin flip? So it doesn't always happen. Look, so as she's flipping the coin, after doing it 10 times, the proportion or the probability was at 40%, right? This is an experimental probability, by the way. But as it kept going, the law of large averages, it ended up getting to, so 5,000 flips, it got to 50%. So that's that long run probability. But this is theoretically, it should be 50%, right? If we did the same thing with a coin, it would be, not a coin, a die. We know that a die is six-sided, so it should be 1/6 probability. So let's go ahead and write down our definition for theoretical probability. It is probability that is determined on the basis of reasoning. And you'll write down all these examples down here. Cards, slot machines, roulette, dice, lottery, etc. All the gambling that you're used to in a casino. Why is this important? Well, theoretical probability is what the people who create these games count on, okay? It's more certain for a casino and for a lottery that they're going to make their money if they have this theoretical probability. Is it possible to get a theoretical probability for weather or meteor or asteroids? It's not. Social media, no, we have too much data as individuals to have this theoretical probability. It's not as simple as saying, oh, well, it has 6 equal probabilities of landing on 1 through 6 on a die. It doesn't work that way. We are not like that as far as humans and a lot of things in real life, okay, sports. But here's some of the examples. Like a lot of this that I have here is what we're going to be learning in class. This is what's going to be on your test, this idea of coin flips and marbles in a bag. What's more important for you as an individual going into the real world? The experimental probability and understanding how that works, okay? But as far as assessments go, we're going to be really diving into this idea of theoretical probability, okay? The last note that we're going to have, using experimental probability. Well, what is this experimental probability? We've discussed it so much. Well, over a long series of repetitions, the experimental probability should be approximately equal to the theoretical probability. If this asteroid hits Earth, right, we will at that point know what the theoretical probability was. Like, it has so many possible routes. Okay, which one is it going to take? Well, if it passes Earth, we knew, okay, now we can get what that true theoretical probability is. So experimental probability's goal is to figure out the theoretical probability, the actual probability that something's going to happen. So theoretical probability is like the actual probability that an event is going to occur. Okay, so we're using experimental to guess and approximate this theoretical. Okay, if we go back to the video, here's the coin flip simulation. You'll notice how this is an experimental probability the whole time, and it's getting closer and closer and closer to the true theoretical probability. All right, this is a 46-minute video. This is us getting started with probability. There's still a lot that we're going to get into as far as book learning and practice problem types. But hopefully this was eye-opening for you. If you get a chance, check out the Social Dilemma. If ask your parents if that is allowable. I know that there is some sensitive material in it and disturbing about politics and stuff, but it's all part of our world right now, and it's something that we need to learn as much about as we can. So let's go ahead and end the video there.